Good afternoon, everyone. My name is Xie Chen. I am a condensed matter theorist at Caltech. And I want to tell you today about how we use the idea of quantum circuits to study the central question of condensed matter theory, which is quantum phase and phase transitions. Is this? Oh, yeah, it works. Right, so the central question in condensed matter for centuries is about phase and phase transitions. Of course, there are phase diagrams that's very well studied, like the one shown here for water. We all know that water can be in solid phase, liquid phase, and gas phase, and there's transition between them. So I'm pretty sure every point on this phase diagram is very well understood. But once we move to the quantum regime, there are a lot of new surprises and a lot of new unknowns. So here we're thinking about quantum mechanical system, especially quantum system at effectively zero temperature. And we're thinking of generically strongly interacting quantum mechanical system, and we ask what kind of phases can we have and what kind of phase diagram there can be. So already from the past decades, we already know that there are a lot of very exotic and very interesting phases like the quantum Hall phase, the superconducting phase, the more traditional ferromagnetic phase, of course, but also the more exotic so-called topologically ordered phase. And then the transitions can be the usual kind of first-order transition, second-order transition, but there are also surprising transitions which doesn't follow the usual rules of how phase transitions should happen. That's what we call something like the deconfined quantum critical point. Okay. So this, of course, motivates a lot of study that you will hear at this conference. So I'm sure you will hear talks about, for example, graphene. This is one of the, I'm just trying to illustrate a way that the discoveries can be made in the field of quantum phase and phase transitions. Let's say we have a graphene and put together and twisted them by an angle. And then in experiment, people see a variety of phase diagram under different parameter space. And then on the theory side, people make predictions and then confirm the theory or confirm the experiment or challenge the experiment, and there's a lot of back and forth going in between, and that's a lot of story you'll hear at the conference. So our approach, rather than starting from specific material, we try to take a more top-down approach, and we try to ask questions in a slightly different way. For example, we say, let's say we consider just generic strongly interacting quantum many-body system. Okay, so it has to be quantum, it has to be many-body, and it has to be, we consider any local but strong interaction to be possible. And then we ask the question of, given the dimension, given the symmetry, and take any local interaction, what kind of phases in principle can exist? Not what phases we already discovered in a material, but in principle, what kind of phases can exist, and how to classify all possible phases, and what are the phase transitions like between all these phases. So these are the more ambitious, the ambitious questions we try to address. Of course, they're very difficult to start with. But along the way, we find a surprisingly useful tool, and that's what I want to tell you about. This is about quantum circuit. Okay. So it turns out that quantum circuit, as a tool that's developed, of course, for quantum computation, help us to think about the definition, even the basic definition of what is a quantum phase. And then from there, we can actually make progress in terms of classifying phases and trying to study their transitions. So starting from definition, it gives us ideas to construct toy models. And then, of course, in order to make connections to real materials and experimental systems, that's a longer way. Ideally, a numerical simulation will take us between toy models and realistic systems. And finally, maybe actual experiment. So this is a longer way to reach experiment. But the good way, the advantage of going from this approach, the more top-down approach, is that it's more systematic and sometimes we get surprises. Okay, so let me try to illustrate to you how this approach can take us somewhere. Maybe not all the way to the experiment yet, but it can help us review structure of the phase diagram that was not already known before. Okay. So let's go back to talk about a little bit about what's the definition of quantum phases, because I said that quantum circuit turns out to be a useful way to help us define quantum phases. Well, quantum phases was defined. This is Subir's textbook of quantum phase transitions, and there's a sentence that says quantum phases basically is a region in the phase diagram where there's no singularity, where everything's smooth, everything remains more or less the same, then that's a quantum phase. In particular, if we're considering phases with a gap, meaning that if we have low-lying ground states and then a finite energy difference to all the excited states, then this is what we call gap phases. And the definition of gap phases is such that we move from one Hamiltonian to another Hamiltonian. And if this can be done while keeping the gap open, so smooth deformation of the Hamiltonian without ever closing the gap, then this is considered a phase. And this is very well understood. This is applied everywhere. But what we thought around 2010 is to take that definition and reinterpret it as an equivalence relation not between Hamiltonians, but rather between its ground state wave function. So introducing state and considering their entanglement structure and using quantum circuit to capture it. Okay, so it turns out that what we realize is that the smooth deformation of gap Hamiltonian without closing gap is actually equivalent to adiabatic evolution between wave function but for a finite time. Okay. And this translates into what we call a finite depth quantum circuit. Okay, so you might be saying, quantum circuit, what quantum circuit? When I say quantum circuit, I literally mean the kind of circuit that people use to build quantum computers. So the quantum computing company or the labs, they take qubits, and then they apply unitary transformations to achieve a quantum algorithm, for example, right? And the kind of quantum gates used can be single qubit unitaries, or 2 qubit unitaries, or 3 qubit unitaries. But eventually, we put all these things together. So let's say here are the qubits. And these blocks, each of them are, let's say, just 2 qubit unitary. Actually, it can be more body, doesn't matter. Here, I'm just drawing 2 body unitaries. And what we can do is to apply these so-called unitary gates. We can apply many of them at the same time as long as they don't overlap with each other. When they don't overlap with each other, they commute, so we can apply them at the same time. And then we can apply another layer. The second layer might not commute with the first, but it doesn't matter. We can just keep applying it. And the number of layers that can be applied is something that you might hear in the news that the quantum computing experiments like to brag about. This is called the circuit depth, meaning how many layers of unitary gates can be applied in a quantum algorithm. Of course, the longer the depth, the larger the depth, the better, because that means you can actually create a lot of entanglement and achieve a lot of quantum computation. Okay. So for us, we are interested in, at least for the first part of this talk, we're interested in a special type of quantum circuit called finite depth quantum circuit, meaning that the number of layers that can be applied is only a finite number, and it's finite, of course, relative to the total system size, the total number of qubits. So no matter how many qubits you have, as long as the number of layers of unitary gates applied is finite, then there's a limited ability for the circuit to generate entanglement between the qubits, and that actually becomes the definition of equivalence relation defining a gapped phase. Okay. So this is our work in 2010, where we proposed that because of the locality preserving property of the finite depth circuit, so we can actually use it as a definition of equivalence relation between ground state wave functions in the same gap phase. So the original definition in terms of smooth deformation of Hamiltonian is equivalently interpreted as finite depth circuit equivalence between ground state wave functions. Okay. And you may say, okay, this is just another way of saying things, but actually it's very helpful because it helps us to think about the entanglement structure in the wave function, which in turn help us to discover new phases. Okay, so let me show you how this is done. So the notion of a finite depth circuit leads to our definition of what's called short-range entanglement and long-range entanglement. Any entanglement can be created by such finite depth circuit is considered short-range, otherwise it's considered long-range. And at the time, around 2010, if you were coming to March meeting back at the time, the heated topic back in the days was not definition of phase. It was about topological insulator. And there was a huge excitement about the discovery of topological insulator. And the very big question back then was the interacting generalization of topological insulator, because topological insulators was discovered in free fermion system. And even better, there was a full classification of what can happen with free fermion system if you have topological band structures. So this part is very well understood. But what people wanted to understand is what if the system is also strongly interacting? Does this classification table still hold if the system has strong interaction, and also whether there are new phases in the presence of strong interaction? And that is not obvious because the free fermion framework using band structure and all that does not immediately address this question. And that's why this quantum circuit idea pertaining to the entanglement structure of the wave function actually help us. So what we realized is that these so-called, now what we call them symmetry-protected topological phases, basically interacting version of topological insulators and superconductors, they have the equivalent of short-range entanglement that can be created with finite depth circuit, but protected by symmetry in some way. Okay, so the entanglement pattern is relatively simple, but they somehow have intricate interaction with symmetry so that they're protected. And this led us to the complete classification of symmetry-protected topological phases in one dimension, and also the construction of symmetry-protected topological phases in 2 and higher dimensions, and involving this mathematical notion of group cohomology. So I don't want to go into any details about how these constructions are done, but I just want to illustrate to you the power of thinking very abstractly, starting from the definition and introducing notions like quantum circuit, and eventually get to some point of discovering new phases. Okay, so that was back then. That was more than 15 years ago. Sorry, and there are of course new questions we need to answer, and that's the second half of my talk. I want to tell you about what we have been working on more recently. So the first part of the talk was about moving between different points in the same gap phase, and we find that this is achieved by the so-called finite depth circuit. And then the next very natural question to ask is how to jump between gap phases, because hopefully, ideally, this would help us to understand phase transitions. So we want to understand what will take us from one point, from one phase to another phase along this red arrow, right? And of course, we know that from the Hamiltonian perspective, what happens is that you tune some parameter in the Hamiltonian, it go across the phase transition, the gap closes, singularity happens, and something dramatic at the critical point, and then the gap opens up and we enter into a new phase. So that's the picture everybody has. But we need to ask the question, we want to ask the question of whether there's an equivalent circuit version describing that process, and whether that circuit perspective can give us new idea of thinking about phase transitions. Right. So it was not immediately obvious. That's why it took us almost 15 years to answer that question, because if we try to follow this adiabatic path, this red line, follow the adiabatic path of the Hamiltonian, we know that the gap will close, and you need to be very slow across the transition point, and the adiabatic evolution needs time that scales at least linearly with system size, meaning that the system size is L, and the gap closes as 1 over L, so the adiabatic evolution takes time also roughly on the level of L. Okay. And it was proven even back in 2006 that if we want to go between phases, interesting phases, but different phases, then a linear lower bound in time, in circuit depths or in just evolution time, is needed. It's definitely needed. That's already known. But that doesn't answer our question. We could have said, okay, then linear depth circuit sounds like the answer, but it's not. It's not that simple. That's why we couldn't answer it for 15 years. And the reason that linear depth circuit doesn't answer the question is because linear depth circuit is actually too much. Okay, it's more than sufficient to do the job. So by linear depth circuit, I mean that you apply layers of unitary gates, and the number of layers goes linearly with the linear size of the system. And when I say that linear depth circuit is more than sufficient, that's because generic linear depth circuit is actually too powerful. It's too much. Because if we have decoupled qubits and we apply one layer of circuit, we might entangle them pairwise into entangled pairs, EPR pairs. And if we apply two layers of circuit, we might entangle everything but into a short range entanglement pattern. But if we apply circuit for linear number of layers, that's going to create entanglement between basically everybody and everybody. So that's going to generate a long-range entanglement. And it's going to lead to what people call entanglement volume law and lead to very high energy states. And people discuss this a lot in dynamics and in quantum gravity about information scrambling and chaos. So even from the words, you can see that this is too much than what we are asking for. What we are asking for is very simply that we want to move between gap phases, but we don't want to leave the low energy region, right? Because in condensed matter, we want to stay zero temperature phases. We want to stay at very low temperature. We want to stay at very low energy. And we don't want to get to very high energy thermal state or excited states. So the generic linear depth circuit would be this dashed black line that takes us all the way to the outside world, while we want to stay on the ground, but just jump between islands. So the question is how to jump between gap phases without leaving the gap region. And the answer, and that's what we figured out in 2024, the answer turns out to be something called a sequential quantum circuit. Okay. So let me tell you what the sequential quantum circuit is. And to show you what a sequential quantum circuit is, let me just demonstrate it with the simplest example of switching between two quantum phases. And this is the prototypical quantum phase that's being taught in maybe condensed matter 101, where we have an Ising chain, just qubits. But we know that the qubits can form different phases. If either we can polarize them all in the transverse direction, or we can add an Ising coupling, so the qubits will try to form a ferromagnetic interaction and try to align with each other. And on the one side, the ground state wave function is simply a product state of plus, 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 plus. On the other side, it's the famous GHZ state where it's a global superposition of all spin down plus all spin up. Okay. And very famously, of course, these are two different phases. If we impose a global Z2 symmetry, and on the left-hand side, we have a symmetric phase, while on the right-hand side, we have a symmetric breaking phase. Okay. So the question now becomes, how do we move from the symmetric phase to the symmetry breaking phase using quantum circuit? And this has been studied because people have, with a quantum computer, they want to build these GHZ state. Supposedly, we start from a bunch of qubits that's not coupled, right? We start from a product state where all the qubits are just polarized in the x direction. And then people with a quantum computer ask, how can I generate a GHZ state out of it? So they already have proposals about what kind of quantum circuit can allow us to do that. And one particular proposal goes like this, that first we do a pi over 4 rotation of this first sigma x, and then we do a pi over 4 rotation of ZZ, and then we do a pi over 4 rotation on the second x, and then we do a pi over 4 rotation on the second and third ZZ, and so on and so forth. But you can see the structure. The structure is such that we're doing 2-qubit unitaries, but one after another, right? We're doing 2-qubit unitary on qubit 1, 2, and 2, 3, and 3, 4, and eventually cover the whole system and to turn the product state into the GHZ state. And that's going to take time because we want to sweep the whole system one step at a time. So this is actually going to be a linear depth circuit because we need a linear number of steps to cover the whole system. On the other hand, this is a very special kind of linear depth circuit because in every layer, we're applying only one gate. And we're applying things sequentially. We're starting from the left-hand side, and we move sequentially from one end to the other, and that's what we call a sequential circuit. Okay. And this sequential circuit actually is more powerful, definitely, than finite depth circuit because it allows us to move, to map x to zz, zz to x, and actually map a symmetric phase to symmetry breaking phase, and backward also back from the symmetry breaking phase back to symmetric phase. Okay. And another example, a very prototypical example, is to map between trivial state to a topological state. And for anyone who have heard about these toric code state, they're very popular quantum error correction codes that people actually use to error corrected quantum computing with. And here the question is, how do I start from a simple product state on a 2-dimensional square lattice and use quantum circuit to map it to the toric code state? So I'm not going to justify any of these calculations, but just claim that somebody figured this out, and the circuit goes like this. So we first apply a bunch of gates in the first row. And all these gates in the first row, they commute with each other so they can be applied at the same time. So that's steps 1. Okay, so one time step, we apply all the gates in the first row. And that generates one minimum slice of topological states out of a product state background. And then what we can do is to apply the same gates on the second row. The second row cannot be done with at the same time as the first row because they don't commute, but we can do them one row at a time. And eventually, for the last row, we just turn our head 90 degrees and then move sideward and eventually close the whole system up. Okay, so no matter how big a system you have, this can always be done. And this is, again, a sequential way of applying a linear depth circuit. And the circuit depth, meaning the number of steps that takes to cover the whole system, scales as Lx plus Ly. So that's another linear depth sequential circuit. Okay. So based on these examples, we propose the general notion of a sequential circuit where it can take you can follow a different sequential pattern from left to the right, or patch by patch, or line by line, or radially. It doesn't matter. It can be all different sorts of pattern. But very crucially, we define sequential circuit to be a circuit where each local degree of freedom is only acted upon by a finite number of gates, such as this one. So here, each qubit is only acted upon by 2 gates, but the whole circuit is very long, right? It takes a linear time to implement. And but the fact that each degree of freedom is only acted upon by a finite number of gates is exactly what we need here, because now if we cut the system into a segment and calculate the entanglement entropy of that segment, we see that entanglement entropy between these 2 dashed lines, they only change by the gates at the 2 ends, right? Here, this gate and this gate. Only these 2 gates change the entanglement of the region, so the entanglement of the region cannot change by much. And that's exactly what we need, because to move between gap phases, we want to preserve something called entanglement area law. And if entanglement area law is preserved, that roughly also preserve the gap of the system. So that shows us that a sequential circuit is actually the answer to our question of how to move between gap phases using a quantum circuit. So what we did in this paper, in this 2024 paper, is to show that actually sequential circuit can map between all kinds of gap phases. I showed you 2 examples previously that's already known, but then we quite meticulously went through all the gap phases we know up to 3 dimensions, and show that a sequential circuit can be designed to move between the phases. Okay, so that's the result here. That says that the sequential linear depth circuit is the answer. That's both necessary and sufficient. Okay, so now right at 5 minutes, and the question is where to go from here. I was advertising this as a sequential circuit, hopefully as a tool to give us some insight into phase transitions. And it's not immediately obvious how this happens, but I want to advertise one idea that might eventually be helpful. This is, of course, still very much work in progress, and this is something I'm very excited right now, which is the idea of sequential circuit as the so-called generalized symmetry. So generalized symmetry, of course, is a very hot topic, but more on the high energy side in the past decade. And you can see that there are a lot of programs and conferences. And here I want to highlight this diagram that people draw for higher form symmetries, showing that it's an intersection between math and quantum gravity and high energy and condensed matter. And I want to insert another one, which is quantum information, although that would be too many layers. But a sequential quantum circuit will be the quantum information perspective on generalized symmetry. So just to say what those words mean, let me say why this might make sense. Because usually when we talk about symmetry, we have a very simple-minded picture of symmetry. For example, let's say the Ising chain, where we say, okay, we have a Z2 symmetry of the Ising chain. What we actually do is to flip all the spins at the same time. Right? That means we apply sigma x, sigma x, sigma x on all the spin at the same time, and that's a tensor product of unitary on all these qubits. So it's a tensor product of local unitaries. But it doesn't have to be this, and already from the study of symmetry-protected topological order, we know that symmetry can be more general, and we can have situation where the symmetry acts like x, 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 tensor product of x, and then tensor product of some 2-qubit unitaries, phase factors, sorry, where did I go? And this is not a simple, as a whole, this is not a simple tensor product of local unitary, but it's a finite depth circuit. So symmetry can be tensor product of unitary, but it can also be a finite depth circuit. And of course, now we want to take one more step and say that symmetry actually can be a sequential quantum circuit. And this idea is already around because this mapping from symmetric phase to symmetry breaking phase, which we usually call the Kramer-Wagner duality, is one of the generalized symmetry, the non-invertible symmetry that people talk a lot about. And here's a review about it if you're interested. And as I showed you previously, here's a quantum circuit implementing that transformation, and as a Kramer-Wagner duality, as a generalized symmetry that people study, this is a very exotic type of symmetry, of course, because the symmetry with its inverse does not go back to identity, but goes back to identity plus something, but that's exactly why we call it the generalized symmetry, that doesn't form a group structure, and blah, blah. And what's amazing about this generalized symmetry, at least in this situation, is that if we enforce the symmetry, it pins down to the critical point. It hold us exactly at the critical point, and this symmetry is an emergent symmetry at the critical point. And that reveals a lot, relates to, of course, the CFT at the critical point, and allows us to go into see the structure. So I cannot go into any detail about that, but I just want to put this out there, that sequential circuit, from what we understand right now, is the lattice version of generalized symmetry, and it relates to all these notions of gauging, duality, non-invertible symmetries, and topological defects, and all these things hopefully eventually will give us deeper insight into quantum critical point at phase transitions. So that's all I want to say. I want to thank all my collaborators and take some questions. Thank you.
Thank you very much, Asia. And questions? So you have the first question.
Yes, of course. Thank you so much. That was fascinating to me because I've thought about this relationship between quantum computing in the circuit model and adiabatic quantum computing, which you mentioned at the beginning. So if the sequential method that you've proposed is the right level of power for this, and it's actually equivalent to adiabatic quantum computing, does this set limits on what we need to consider in terms of our quantum circuits? Is the model you propose that's too powerful also too powerful for most quantum computing applications?
That's a very interesting question. So this idea of adiabatic quantum, if I understand correctly, there was a proposal about using adiabatic quantum evolution to go from, let's say, product state into some many-body entangled wave function, which potentially solves some factoring algorithm, right? In those kind of situation, I'm not exactly sure that the answer is the adiabatic algorithm is equivalent to sequential circuit, because in those kind of situation, I doubt it can be a local gap Hamiltonian. I mean, the end result, let's say the equivalent of, if we want the eventual state generated, the answer of factoring algorithm to be the ground state of a Hamiltonian. I don't remember, I learned it back in the days, but is that a ground state of a simple field body local in a finite dimension Hamiltonian? If that is, then I think then there will be a sequential quantum circuit. But in general, I think it's probably not. Otherwise, it will be too easy.
Okay, thank you.
Yeah, we should talk more.
Next question.
Thank you for the nice talk. I have, I guess, two closely related questions. The first is that generally, at least in 1 + 1D, I can think about getting between gapped phases as some combination of gauging and stacking an invertible theory. Do you think any such transformation can be implemented as a sequential quantum circuit? And the second is, do you have a sequential quantum circuit for fermionization?
Yeah, great question. So I think the answer to those are probably yes, at least in one dimension. Yeah, in one dimension, there's a much better understanding of this so-called, I didn't mention it, but there's underlying all these, there's this symmetry TFT picture and how all the duality transformation, including bosonization, fermionization, gauging, and all these. And then the paper, we had a later paper about this one is about duality. There should be one paper about duality and sequential circuits. So the answer in 1 + 1D, at least I think it's probably yes. In higher dimension, I would suspect it's also yes. There are a lot of, in higher dimension, like gauging is also sequential circuit that we know. Yeah.
Thanks.
Thank you for the nice talk, Mike. I have a question about when you apply a sequential circuit, I think you are jumping from one RG fixed point directly to another RG fixed point, right? But so by RG fixed point, I mean the correlation length is 0. But if you deform the Hamiltonian instead, the correlation length will diverge and then go back again. So can this be formulated using this kind of circuit?
Yeah, a great question. So these are all very expert questions. So exactly, if we just have purely local gates, then the correlation length if the correlation length was 0 before, then it will stay 0, but it can just decay at a longer size. But so we're playing some trick here. So we're saying, okay, we just use sequential circuit, but then if we want to move away from those fixed points, you can introduce the correlation length using a finite depth circuit or adiabatic evolution that way. Yeah.
There's some generalization of a finite depth circuit which allow exponential tails or something. Can this also be applied in this case?
Yeah, potentially, yeah.
Okay, thank you.
Hi.